Hello, this is Saswata Bhattacharya from the Department of Material Science and Metallurgical Engineering at IIT Hyderabad. I will be teaching this course on Thermodynamics and Kinetics of Materials. So, why do we study thermodynamics? Because thermodynamics provides the fundamental principles that govern the behavior of matter, and also it provides a rational basis for organization of information about materials characteristics, and it also gives you a way to identify fundamental properties or calculate fundamental properties from which all other properties can be calculated. Thermodynamics is comprehensive, that means it covers the behavior of all matter, that is it covers or it is capable of handling all classes of materials, whether it is a metal, whether it is alloys is a mixture of metals, and then ceramics can be oxides, carbides, etc., and then polymers, composites, solutions. Basically, you can have solid solutions where one solid component acts as solvent and other solid components as solute, and then you can have liquid solutions, and you can have also solutions such as one solid is dissolved in one liquid. And then there is crystals with defects, and then you can look at crystals with defects. For example, we can control the amount of defects in a crystal, for example, controlling the amount of vacancies at a given temperature. And then you can have gas mixture and all these types of. So it covers, basically it's so comprehensive that it covers all classes of materials, and it's also capable of handling all effects and influences. That means it can take into account how a material behavior will change when there is when it is subjected to a thermal field, or it's a temperature field, or a certain temperature rise or something like that, or it is applied, or some mechanical stresses are applied, or some pressure is applied. And then, for example, if the chemical composition is altered, or if there is a chemical reaction between certain components, then the electrical, so you can also apply electrical field to modify the thermodynamic properties. For example, in a ferroelectric material, you can basically apply electric field to modify the equilibrium states or equilibrium states of the material. Similarly, we can apply magnetic field to control the equilibrium magnetic states in a material. So, states of matter, in general we know about states of matter like solid, liquid and gas, as you know that there is something more than a state that comes in thermodynamics, and that is the definition of a phase. So a solid can contain multiple phases, and each phase can contain multiple components. So since a phase can contain multiple components, so I can have a solid which is composed of multiple phases. So what is a phase? A phase is a chemically / structurally, means is basically both chemically homogeneous as well as structurally homogeneous state or portion of a material which has physically distinct properties and which is mechanically separable from other portions of the material. So basically, if I look at this diagram, so I am mapping different phases. Say I have a material and I am looking at a microstructure, a small representative volume of a material, a small volume element of the material. Now in that small volume element, say for example, I have like different phases, and say this is alpha phase, this is alpha phase, and this is alpha phase, and the surrounding is beta phase. So each alpha phase will be structurally and compositionally homogeneous, and it will also have distinct physical properties than the beta phase. It means, for example, it will have a different density than the beta phase, lattice parameter, alpha phase will have a different lattice parameter than the beta phase, and elastic constants can be different, refractive index can be different. So this is how you can define these two phases, alpha phase and beta phase. Now the interesting part of thermodynamics is that it provides a rational way to map equilibrium phases of any material as a function of various influences. For example, thermal influence or mechanical influence or coupled influence like thermomechanical influence, etc. So when we design a material, we have this relation between process, structure and properties. Structure can be a microstructure. Microstructure again, if I take a small representative volume element of the material or statistical volume element of the material, I can now observe under a microscope. I can identify different regions. Some regions are I can identify distinct regions. If a material is completely homogeneous, it has a single phase, then I will not be able to see any feature. However, if under a microscope I am looking at a material which has multiple phases, say for example I take again the small volume element and I see, say for example, one region which I can identify as a beta phase and then the surrounding is an alpha phase, you see there is an interface. So basically thermodynamics basically rationalizes means how to describe this microstructure in terms of equilibrium phases like beta phase and alpha phase, and also based on how the phases are distributed in this microstructure, like alpha beta phase is appearing as a droplet inside alpha matrix, it will determine some of the important physical properties. For example, the overall density of the material, or overall stiffness of the material, or overall strength of the material. So as a result, as you can see, thermodynamics plays the central role, the structure of determining the phases that are present in the structure. So here only thermodynamic principles can be applied to identify principles basically dictate the phases, right, the phases that are available, and also how are they distributed in space, and what's the volume fraction or the relative volume fraction of each phase, etc. So thermodynamics basically can be used to answer several practical questions. For example, if I take an alloy containing, say, three metals, say for example titanium, aluminium and niobium, and if I ask a question that this alloy that contains titanium, aluminium and niobium, and I am heating it at a temperature of say 1100 degrees Celsius at standard atmospheric pressure, will it oxidize at that temperature? So this is some practical question. So that titanium or aluminium or niobium can react with oxygen, or all of them can react with oxygen forming titanium or alumina or niobium oxide. Similarly, so I am telling an alloy of titanium, aluminium and niobium, will it oxidize at a certain temperature, say 1100 degrees Celsius at 1 atmosphere pressure. Similarly, I can ask, if I take a polymer blend, for example, a polymethyl methacrylate, which is PMMA, and PVDF, I have made this blend at some high temperature. Now I take it down to say something like at say 50 degrees Celsius. Then, and I keep it at 50 degrees Celsius for some time, will it phase separate? So that means it will separate into two distinct phases. One is PMMA, another is PVDF. So such information can only be obtained when we can, if we apply the thermodynamic principles that I am going to teach in this course. So what are the learning objectives? Let us look at that. So we first have to understand what do you mean by thermodynamic description of materials in terms of components and phases, and what are the thermodynamic variables that we will use to describe such systems. Then we will look at the principles of phase equilibria, that is, what are the, say for example, in simple thermodynamic systems, what do you mean by thermal equilibrium, what do you mean by mechanical equilibrium, what is chemical equilibrium. So for example, thermal equilibrium, I can think of one block of copper that I take at say 50 degrees Celsius, one block of copper at 100 degrees Celsius, and I take them together and I put them together in contact. What will be the temperature, finally the temperature of this entire system of these two copper blocks. So something like that. And similarly, if I look at mechanical equilibrium, I am looking at a condition where the sum of forces go to 0. I can also define chemical equilibrium in terms of with, say, I have one species, one system with a species concentration which is like 50%. In another case, that same species has a concentration of 20%. Now, if I take them together and I put a membrane that allows exchange of matter, what will be the equilibrium concentration of that particular species. So, also we will learn about the criteria for phase stability. That means whether when I form a phase, whether this phase is stable at a particular temperature or metastable, or is it unstable. If it is unstable, then it will decompose into some other phases, right? It will transform into some other phase. So, what we will also understand, since we look at this equilibrium like thermal equilibrium, mechanical equilibrium, chemical equilibrium, thermal equilibrium basically means that if there is a temperature difference, we will see that there is something called heat transfer. So, it will dictate the driving forces. So, I will learn about the driving forces for heat transfer, driving forces for diffusion of species and so on. So, basically we can define the driving forces if we understand the principles of phase equilibrium, and I can and that thus I can basically, if I know the thermodynamic driving forces, I can also assess the feasibility of any process. For example, feasibility of oxidation of a certain alloy, or feasibility of corrosion of a certain alloy in a condition where it is surrounded by salt water, it is immersed in salt water. Moreover, we can think of bulk thermodynamics. Bulk thermodynamics is basically when I am assuming a material system or a material which does not have surfaces, or the influence of surfaces is negligible. And then I can also look at the effect of surfaces, which is basically covered in surface thermodynamics. Finally, what I will do is I will connect this thermodynamic driving forces with fluxes, and I will basically then elucidate or basically describe the principles of kinetics. That is, I will finally, if I can define the driving forces, I will connect it to flux of species, and I will find out the rate at which. So, basically thermodynamics, if you look at thermodynamics does not, the equilibrium thermodynamics does not consider any rate. So, it does not consider time as one of the parameters. So, at any given time or at any point of time, I can apply thermodynamic principles to understand equilibrium. But when it comes to kinetics, when I am connecting fluxes to forces, what I am trying to understand is that how fast or how slowly one process will evolve to equilibrium. So, how long it will take to achieve certain equilibrium, or how far away we are from equilibrium. So, all these cases we can, so if I want to see, say for example, at what pace a reaction will proceed. So, whether the reaction will, so basically simply put, whether a particular reaction is possible or not, that will be governed by thermodynamic principles. But how fast or slow the reaction will proceed, that will be governed by these kinetic principles. So, we will finally describe these kinetic principles by connecting driving forces to fluxes of species. So, this is the syllabus. So, you can go through the syllabus. Syllabus I think will be uploaded anyway in the system. So, as I told you, first module. So, I have made it modular so that every time, every part of the syllabus I will explain, and then I solve a few problems in each part so that you are clear about the concept. So, I will talk about, so in the first module, I will talk about the thermodynamic systems of variables and how to describe the state, and then the laws of thermodynamics, the first law, and some definitions like internal energy, enthalpy, heat capacity, etc. And then second law, which will describe which basically gives the idea of directionality of a process, and so basically whether a process is spontaneous or not, or whether a process is reversible or irreversible. And there I will give an introduction to the concept of entropy and its statistical interpretation. Statistical interpretation means I will connect all these thermodynamic quantities with the microscopic description of matter, that is in terms of atoms and molecules. And finally, I will describe the third law, which will define a scale, absolute scale of temperature. Then I will look at the concept, I will describe the concept of reservoirs and different thermodynamic potentials. So, we often use reservoirs when describing equilibrium in a system. So, for example, a pressure reservoir or a pressure and temperature reservoir. So, when I have a pressure and temperature reservoir, for example, we define something called Gibbs free energy, which is a very, very important quantity in materials thermodynamics. So, often we look at a given temperature and pressure, and often we look at the minimization of Gibbs free energy that gives rise to equilibrium states. I will also describe some of the thermodynamic relations and how Maxwell's relations can be used to basically derive not directly measurable thermodynamic quantities from directly measurable ones. Directly measurable ones are like temperature, pressure, heat capacity, thermal expansion, compressibility, but not directly measurable ones are like chemical potential, Gibbs free energy, etc. Then in module 2, I will look at the governing principle for thermodynamic equilibrium, and this is the principle. This Gibbs phase rule is the principle, and it is used to construct phase diagrams to understand the equilibrium maps of phases, and I'll also talk about stability, like stable, metastable, and unstable equilibrium. Then I'll go to unary systems, where I'll define some equations like Clausius-Clapeyron, which will dictate at how pressure and temperature can influence boiling point, freezing point, or melting point. And then I look at the thermodynamics of solutions, where I'll define something called partial molar quantities, activity, etc. And then I'll look at Gibbs-Duhem relation, and also some of the models that are used to describe these solutions, to describe the solutions, and how these models can be used to understand clustering and ordering of species, or clustering and ordering transformation. So, in module 3, I look at we will describe Gibbs free energy composition diagrams in binary systems. So, we'll focus mainly on binary systems. We can also give a few examples of ternary systems, but we will not go beyond that in this course. We will restrict ourselves till ternary systems. But once we are clear with binary and ternary, you can extend this knowledge to understanding multi-component systems. So, here we look at how these Gibbs free energy composition diagrams can be used to define thermodynamic driving forces. Gibbs free energy composition diagrams can be used to understand equilibrium between phases, and how to use these to construct binary phase diagrams. And also, I look at the experimental determination of binary phase diagrams using cooling curves, X-ray extraction method, or electrical resistivity method. So, I'll give some description, and I'll also do some numerical modeling, some few examples of how we can use these different solution models and solve them to get to obtain phase diagram or equilibrium between phases. And finally, I'll also describe thermodynamics of reactions, where I look at the stability of oxides using some as a function of oxygen partial pressure and temperature, where I will describe Billingham diagram. Then I'll look at thermodynamics of surfaces, where I will describe absorption of gases, Langmuir isotherms, and gives interfacial thermodynamics. And finally, I look at the thermodynamics of irreversible processes, where the rates come in and the rate of entropy production comes in, which gives a relation between flux and thermodynamic driving force. And then I'll give some basics of diffusion. So these are some of the texts that we will follow. So one of the texts, this is a classic text, Thermodynamics of Solids by Richard Swelling, and then also De Hoff's text on thermodynamics in material science. These are two texts that I will follow in general. However, you are encouraged to also read Alloy of Phase Equilibria by Alan Prince, which is a very classic book. It is actually available in MSI Port. Then there are also some of these books like Baluffi's book on kinetics of materials, and Porter Sterling phase transformations book, and also this very interesting monograph by Hillert and Celebi, where basically they describe how to use thermodynamics, how to compute using thermodynamic principles. So basically this is a course on this book describes computational thermodynamics that will be so that gives you aspects of numerical modeling of free energies to obtain the phase diagrams. So I hope in the course that follows, you will be able to enjoy the course, and you will be able to understand some of the key principles, some of the and you will be also able to apply these key principles to design materials, to solve problems involving materials design, involving materials phenomena, to understand materials phenomena.